Assalamualaikum everyone, I hope you all are doing well and taking good care of yourselves. This is your instructor Ali Faruqi and you are watching Science with Ali. So in today's video we're going to be taking a look at states of matter part 2, which includes the heating and cooling curves and the diffusion. And also we're going to be talking about gas volume, temperature and pressure. Now I have changed the look of our videos. This is my first video with face cam and this new setup, so it's a big change and we'll get along. I hope we get along well on this setup as well. So let's get started. So first thing we're going to be looking at is heating and cooling curves. Now this right here is a heating curve. A heating curve is basically just one singular thing. You need to just keep this in your mind. A substance is changing from a solid to a gas. Now in order to represent that change visually, we use a heating curve. Now there are a few stages in heating curve. For example, when the solid turns into a liquid, there's melting involved, there's boiling involved, and also when the liquid turns into a gas, there's evaporation involved and vice versa. So let's get started with the explanations. Okay. So heating and cooling curves help us illustrate how temperature changes impact changes in the state of matter. A heating curve shows how the temperature of a substance changes as it's heated over time. Now at the start, the substance is solid, right? Over here the substance is solid. Now the temperature is a bit low over here because when you're at a solid, the solid needs to heat up in order to turn into a gas. Now at the start, the substance is solid. It warms up over at this stage, but it is still a solid. And particles inside shake faster, they vibrate faster, right? Now when it reaches the melting point is right here, which is this line, right? The black line which I've highlighted here, that is the melting point, right? It starts turning from solid to a liquid. At melting point, the solid starts turning into a liquid, right? Now the temperature stays steady and heat goes into the breaking bonds. I think you have heard this in physics. It's called lattice heat energy. Right? Because the energy is going into breaking the bonds, the temperature is not increasing. Now during the melting point, what happens is what we talked about was that temperature stays constant and energy goes into breaking the bonds, right? I hope I have made myself clear. Okay, so now let's move on to liquid. So what happens in liquid? Now the state is fully liquid and the temperature goes up as it gets heated. The particles move more freely and the state changes during this state, right? Now at the liquid state, the particles are randomly arranged and they are present in clusters, right? The particles are present in clusters. Now at the boiling point, it changes from liquid to gas. This right here is called the boiling point. I've written it as BP, okay? The temperature stays constant because heat is breaking the force between the particles. As I have written over here, the energy which would be going to the temperature increase is now going to the breaking of the bonds, meaning that the temperature is not rising. Now after boiling, the state change becomes a gas, right? And now in the gaseous state, there is particles move around freely, they are bumping into each other with a lot of energy, and this curve helps us understand how temperature links to a substance state, that is solid, liquid and gas. During a change in state, you need to remember that temperature remains constant. Now moving on to the cooling curve. Now during a cooling curve, you need to understand one thing. We started the heating curve with a solid and we ended it with a gas, right? During a cooling curve, we will start with a gas, and we will stop at a solid. Okay? So what were the processes involved in the heating curve? We're going to be doing the exact opposite of that in reverse order, right? So for gas, what happened was we did boiling point. So this is the boiling, this would have been the boiling point and this would have been the freezing point now, right? This is the condensing. Gas condenses at this stage. Condensing. And the solid and the liquid becomes a solid at a freezing point. Alright, so in a cooling curve, the temperature of a substance is decreasing and it shows how the substance changes from gas all the way to a solid, right? When the substance cools down, it goes to the reverse of what happens in a heating curve from gas to liquid to solid. The horizontal sections on the curve represent moments when the substance is changing its state, but the temperature remains constant during those changes, which I've highlighted over here. This is the freezing point and this is the condensing point, right? Now, moving on to gas volume, temperature and pressure, the second topic of today's class. Okay, so moving on to gas volume. In O levels, gas volume represents, let me write the definition over here so you have some context of what I'm saying. It refers to the amount of space occupied by a gas, right? So it is the amount of space which is occupied by a gas, right? So the volume of a gas is greatly affected by changes in temperature and by changes in pressure. Now when you increase the temperature of a gas, we will be discussing temperature first because I have drawn a very beautiful fire over here, right? So when you increase the temperature in a gas cylinder, what happens is that the particles will gain kinetic energy and this will result in them moving more faster and faster inside the cylinder, bumping into the walls of the cylinder, bumping into other particles, and this causes the gases to collide more frequently and with greater force, right? So this pushes them further apart and pushes them against the container walls. As a result, the gas expands and takes up more space. So a higher temperature, this needs to be written, a higher temperature means increase volume. Sorry, I lost myself there a little bit. Apologies. Right, so a higher temperature means a higher volume. So let's just get rid of the fire because we're done with the fire. And this arrow as well. Moving on to volume. Moving on to pressure. Right? So I have drawn a piston over here. As you can see, I have drawn a piston over here which I have selected right now. Now when I increase the pressure on this cylinder, you are basically squeezing it. This makes the gas particles come closer together, reducing the space they occupy. So a higher pressure leads to a decreased volume because the particles are now more congested, they have less space to move around. This will result in a lesser volume overall, right? Conversely, decreasing the pressure, if I move the piston back up again, the gas particles have more space to move around, meaning they cover more space. As you know, the gas volume refers to amount of space occupied by a gas, right? So when I take the piston upward back again, what happens is that the particles have more space to live, meaning they can occupy more volume, they can relax a little bit and live their life, right? Now in summary, let's just write this down as well. So a higher pressure leads to lower volume. This leads to a lower volume, right? As we discussed right now, right? So the big boy is next, diffusion. All right, so in diffusion what happens is, diffusion is the process where particles, typically gas or liquid molecules, spread out from an area of high concentration to an area of low concentration, right? Typically gas or liquid molecules, because as you know a solid can't flow, so only gases and liquids can take part in diffusion. Now as we know, the kinetic particle theory says that all matter is made up of tiny particles in constant random motion, right? All particles are made up in constant random motion. Now when particles are in a high concentration, like in this area over here, this is a high concentration and this is a low concentration area, right? So what happens is that they collide and exchange energy as they collide more frequently, right? And they move more randomly. So some particles gain enough energy to break away and move to areas with lower particles. For example, there is a barrier in between these two rectangles, right? So if I draw another molecule so I can explain this to you right now. Now when this particle collides with all these other, what happens is it gets enough energy to break away and come over here, right? So it moves to areas with lower particle concentration. This continuous motion and collision process causes particles to spread out until they are evenly distributed. What will happen now is that all the particles, for example 1 2 3 4 5 6 7, okay, I have 7 over here and I will draw 7 over here. 1 2 3 4 5 6 7, right? I have drawn 7 over here and 7 over there. Now the process, now the reaction is now balanced, right? So this continuous motion causes particles to spread out until they're evenly distributed, completing the process of diffusion. This was pretty straightforward. You just need to understand one thing, that diffusion refers to high concentration to low concentration, right? Just keep this one thing in mind. We're going to moving on to the last topic of our lesson, which is the effect of MR on diffusion, right? Okay, so to explain the effect of MR on diffusion, I need to give you guys a scenario first, which is if I line up two people in a race, one is a skinny guy and one is a fat guy, right? So what will happen in a race? Obviously the skinny guy will win because the fat guy has more mass to carry along with it, so means he will be more slower. In the same case, in our periodic table there is something called MR, molecular mass. It stands for molecular mass, right? So if a gas has more MR, means it is heavier, meaning that heavier gas particles are able to move slower and will cover lesser distances than lighter ones. For example, helium has an MR of 4 and oxygen has an MR of 32, right? So obviously oxygen will take more slower time to reach the finish line, which I've drawn over here. So let's simulate this race real quick because I want to do it. Why not, right? So I have helium. Helium will go ahead and by the time helium is at the finish line, the oxygen molecule will be somewhere around here, right? Oxygen molecule will be somewhere around here and helium will have finished the race. Yay, confetti, right? So this means that a gas will diffuse more quickly when it has a lower relative mass. For example, helium is a very light gas, as I've told. Oxygen has a relatively high MR compared to helium. Therefore, helium gas moves faster and covers greater distances than oxygen gas because helium is lighter. So let's write a general rule over here. The general rule is that lower mass lower mass, just write mr in the bracket, mr equals lower mass equals to faster rate of diffusion. Just write that, faster rate of diffusion, right? Alright, so this concludes our topic of states of matter part 1. If you have any questions regarding this video, you can drop them down in the comment section down below, and I will try and respond to each and every one of your queries. Also, drop the comment below of this thing as well, that how do you like the format of our videos now. This will now be the format our videos will be filmed in now, because I was done with that old one. It was very clunky, that old one. This is way better, right? So I hope you enjoy this video, and I will be looking forward to your thoughts in the comment section down below. I will see you in the next class.